Returning to our introductory example, we see that the score for policyholder I is then beta 0 plus beta 1 times x1 plus beta 2 times x2 and so on until beta 7 times x7. Then, as we said before, the exponential of beta 0 is the annual claim frequency for the reference class, which is a male driver aged between 31 and 60 years old, who's living in an urban area, who pays the premium once a year and uses the car for private purposes. But for instance, the exponential of beta 0 plus beta 1 then becomes the annual claim frequency for a man who's younger than 24 years old, who lives in an urban area, pays the premium once a year and uses the car for private purposes. Let us now move on with the estimation of the regression parameters. We apply, as before, the concept of maximum likelihood estimation to obtain the estimates of our unknown parameters beta 0 up to beta p. Ki is once again the number of claims filed by policyholder I during his observation period, with an exposure equal to di. The associated likelihood function, as a function of the parameter vector beta, is then the product over all observations or policyholders I of the probability that the random variable ni takes the value ki. Thus, we need the probability that, under our assumed Poisson regression model, policyholder I reports the observed number of claims ki. Of course, we use here the Poisson distribution, with mean lambda I expressed as the exposure to risk times the exponential function of the score of policyholder I. The maximum likelihood estimator of the parameter vector beta maximizes this likelihood. Now, in contrast to the marginal Poisson regression model that we started with, it is now no longer possible to solve these maximum likelihood equations analytically. Therefore, we will solve the likelihood equations with a numerical technique. In this case, we use the Newton-Raphson method. Say u of beta is the gradient vector of the logarithm of the likelihood. That is the column vector which contains the first-order derivatives of the log likelihood. One can show that this gradient vector can be expressed as shown over here for our specific Poisson regression model. Next to the gradient vector, we also need the Hessian matrix, which contains the second-order derivatives of the log likelihood with respect to the parameters in the vector beta. Again, we can work out these second-order derivatives and show that the Hessian matrix for the Poisson regression model is given by the expression that you see over here. Now, the maximum likelihood estimator of the regression parameter vector beta solves the set of equations that is specified by putting this gradient vector equal to 0. Numerically, we find a solution for this set of equations using the so-called Newton-Raphson approach. That's an iterative method where we update our current solution, beta hat in step r, to become the beta hat in step r plus 1, and we do that using the following expression. Filling in the expression for the gradient vector and for the Hessian matrix, we get our next update. And this iterative method stops when the difference between subsequent solutions becomes small enough. Do note that your statistical software package, which implements generalized linear models, will report you whether this iterative estimation method has reached convergence or not. This is one of the first things you will check when building GLMs for predictive modeling. We continue with discussing statistical inference in the framework of Poisson regression models. And we first focus on setting up a confidence interval for a single regression parameter beta j, as well as performing a hypothesis test for a single regression parameter. Remember that we also covered these steps in the linear regression framework that you studied in traditional econometrics courses. For the construction of such a confidence interval in the Poisson regression model, we will rely on the theory of asymptotic normality that applies to estimators which are obtained using maximum likelihood estimation. First of all, the asymptotic covariance matrix for the estimator beta is obtained as minus the inverse of the Hessian matrix. Using the asymptotic normality expression that you can see over here, we can then write down a confidence interval at level 1 minus alpha for each of our beta j's. In this expression, the sigma hat squared is the element on position jj in the covariance matrix of beta hat, and the z is an appropriate quantile from the standard normal distribution. We continue with discussing a hypothesis test for a single regression parameter beta j. Again, you've seen this before in typical econometrics courses where linear regression models are covered. Now say that we want to test the following null hypothesis. Beta j is equal to 0 versus the alternative hypothesis where beta j is different from 0. Failing to reject this null hypothesis would suggest that this variable corresponding to regression parameter beta j is not relevant when explaining the expected number of claims. We're going to use the following test statistic, denoted with capital T. This test statistic is approximately standard normally distributed under the null hypothesis. Depending on the statistical software package that you are using, you will use the test statistic T, that's what R does, or you will use T squared, that's what SAS would do. Rejection of the null hypothesis occurs when the observed value of T is large in absolute value, or when the T squared is large. An associated p-value will be reported by the statistical software package. When working with factor covariates, a hypothesis test that is very interesting is one where multiple regression parameters are involved. For example, we could test the hypothesis whether the H covariate, which is coded in our example with 3 dummy variables, has a significant impact on the expected number of claims. But in order to perform such a hypothesis test, we will use a drop-in deviance analysis that is based on the so-called deviance statistic. We first explain this deviance statistic. Denote with the calligraphic L of head lambda the model likelihood. That is the likelihood of the Poisson regression model under consideration. So that's the likelihood that we build for our specific model. The maximum likelihood that can possibly attained under the Poisson assumption is denoted with the calligraphic L of k. And this is obtained by replacing each lambda I with ki, where ki is the number of claims reported by policyholder I. We call this likelihood the saturated or full model likelihood. This is a model that is not explaining the data. It is a full model which is just replicating the data. The so-called deviance statistic is then defined as the likelihood ratio test statistic for the current model against the saturated model. It is a likelihood ratio statistic, thus it is equal to -2 times a ratio of 2 likelihoods, as you can see over here. If we fill in the expressions from our previous sheet, then we obtain an explicit expression for the deviance in our specific Poisson regression model. Note that the smaller this deviance is, the better is your current model, in the sense that its likelihood will get closer to the likelihood of the saturated or full model. And we now explain how this deviance statistic can be used to test a hypothesis on a set of parameters. For example, say that our null hypothesis is of the following form, and the alternative hypothesis looks like this. That means that p minus q parameters in the original regression parameter vector beta were put equal to 0. We could use this kind of hypothesis test, for instance, to check whether the complete categorical covariate H should be incorporated in the Poisson regression model for claim frequencies or not. Say that D0 or D0 is the deviance of the Poisson model under the null hypothesis, and D1 is the deviance of the model obtained under the alternative hypothesis. Our test statistic then becomes delta, that is equal to D0 minus D1, and we call this the drop in deviance test statistic. At the bottom of this sheet, we work out explicitly this drop in deviance statistic using the expression that we build up on the previous sheets for the deviance. Using results from mathematical statistics, one can show that the drop in deviance test statistic follows a chi-square distribution with p minus q degrees of freedom. And recall that this p minus q is the number of regression parameters which were put equal to 0 in our null hypothesis. Now, the null hypothesis is rejected in favor of the alternative hypothesis if the observed value of the test statistic is too large, which means larger than the 1 minus alpha quantile from the chi-square distribution with p minus q degrees of freedom. Later on, we can give explicit examples on the use of this drop in deviance analysis when building generalized linear models. Now, this chi-squared approximation to the distribution of the likelihood ratio test statistic is valid only when we consider nested hypotheses. With nested models, the set of covariates that is used in the null hypothesis must be a subset of the covariates that are used by the model in the alternative hypothesis. With non-nested models, we cannot make use of likelihood ratio test statistics for model comparison or model selection. Information criteria, like the Akaike information criterion or the Bayesian information criterion, are then useful to compare regression models. You know that we defined these information criteria in traditional courses on econometrics where linear regression model is covered. Now, let's conclude our discussion of Poisson regression modeling for claim frequencies by returning to the example with portfolio data. The output of this example is discussed in the book by Michel Denuy and co-authors on pages 73 up to 79. It's interesting to know that the authors of this book used the proc GenMod in SAS to analyze their data on claim counts. And we will now discuss some of the output obtained with this particular software package. So here is the specification of the Poisson regression model for the number of claims reported by policyholder I during his period of exposure, DI. Now, the table on the sheet shows us the results of the Poisson regression model using the following set of covariates. We use the interaction between gender and age. We use the district where the policyholder lives, whether he splits the premium, and how he uses the car. The first column in the table lists the name of the variable under consideration. The second column displays the levels of our factor variables. We then see the estimates of the regression parameters, their corresponding standard errors, the lower and the upper bound of the Wald 95% confidence interval for the unknown regression parameter beta j. We see the corresponding chi-squared statistic and the p-value of the associated hypothesis test for the null hypothesis that beta j is equal to 0. Note that we discussed the construction of this confidence interval before, and we discuss the corresponding hypothesis test for a single regression parameter. We summarize here once again the output of our Poisson generalized linear model as displayed in the table on the previous sheet. Please take a moment to check the meaning of the columns of this table, as we explained when discussing our model before. Now, how should we decide upon which explanatory variables should be included in the Poisson regression model? So which variables should we select in our final regression model? Well, to decide upon this, we will use the tool of the drop-in deviance analysis. And here you see two possible strategies for the SAS-proc GenMod or any other statistical software package of your choice to take this decision. You can start from a simple model with only an intercept, and then you can include one additional explanatory variable in each successive step. This approach is in SAS called a type 1 analysis. Or you can start differently from a model incorporating all the available information, and then you exclude irrelevant explanatory variables. That is often referred to as a type 3 analysis. The advantage of the type 3 analysis is that it does not depend on the order in which the terms for the model are specified, whereas the type 1 analysis does. Type 3 compares the complete model with the different submodels obtained by deleting one of the explanatory variables. That is like a backward model selection technique. The type 3 analysis does not depend on the order in which the terms for the model are specified, whereas a type 1 analysis does. Type 3 compares the complete model with the different submodels obtained by deleting one of the explanatory variables. That works like a backward model selection technique. Now, continuing our example, we obtain the following output for the type 3 analysis. The interaction between gender and age in the table refers to the hypothesis test, which compares the full model using the 4 listed covariates to a model without the interaction effect. The degrees of freedom used in this test is 7, because the coding of our interaction requires 7 dummy variables and thus 7 parameters. The observed test statistic takes the value of 75, and the corresponding p-value is very small. Thus, the interaction between gender and age is highly relevant in explaining the expected number of claims. Note that the p-value is calculated as the probability that a chi-square distribution with 7 degrees of freedom takes a value that is larger than 75.16. This probability is, of course, very small. We conclude from the table that all our explanatory variables are statistically relevant and should be kept in the regression model. Now, when going back to our output on one of the previous sheets, we see that some levels of the categorical covariates have a p-value that is larger than, say, 5%. Therefore, we will consider some regrouping of those levels. And to do this regrouping, we use a hypothesis test which verifies the equality of the regression parameters. For example, our null hypothesis then becomes of the following form: beta j1 equal to beta j2 versus the alternative hypothesis where beta j1 is different from beta j2. Once again, a likelihood ratio test will be used to compare the models under the null versus the alternative hypothesis. We could, for instance, test whether the parameter for female drivers older than 60 should be equal to the regression parameter which represents the female drivers between age 31 and 60. If this null hypothesis cannot be rejected, then we will group both groups of drivers into one larger group. In statistical software packages like SAS or R, this kind of hypothesis testing is often denoted with the term a contrast statement. Now, after regrouping our levels of the explanatory variables, Michel Denouy and co-authors report the output from their final model. And you can see over here that all the levels of our categorical covariates now reveal significance. To conclude, here is what we covered in this lecture. You should now have acquired some basic understanding of a first example of Poisson regression for modeling claim frequencies, model formulation, model estimation using the technique of maximum likelihood estimation, how to do statistical inference, how to construct confidence intervals, perform hypothesis tests, and the concept of a drop in deviance analysis. You should now understand how to interpret certain output from statistical software package and how to use the resulting regression model.